How does the pressure beneath the surface of a liquid depend on the depth beneath the liquid and the density of the liquid? Those of you who enjoy swimming and diving beneath the surface of a swimming pool will probably have a good idea of what goes on here, because as you dive deeper, you feel a greater pressure acting on your ears, and that's why they pop occasionally if you go very deep. And so let's find out the reason why. So here's the surface of the sea, let's say, and a quick little boat for you. There we go. And we're going to have a little person here who's diving with his scuba gear on down below. Now, above that diver, there is a column of water. And that column of water has a mass. And gravity acts upon that mass to create a force called weight, which pushes down. And that weight will be pushing down on the area at the bottom of the column. So we've got a kind of situation where here's the area and the weight force is pushing down on that area, and that creates a pressure. Now, just to remind you that this is the same thing which happens, for example, when you push a drawing pin into a wall. You can create a very large pressure at the tip of the drawing pin because the force that you use to push into the wall is acting on a very small area, producing a very large pressure, and that's why it goes into the wall. So what's happening here? What happens if that diver goes deeper? Okay, so here we are. And now we've got a lot more water above him or her, which means that the weight is much bigger weight, and therefore a bigger weight acting on the same area means that we have a higher pressure. Higher pressure. That pressure, by the way, will be acting in all directions on that diver. So we can say here that the deeper you go into a liquid, the greater the special name here, hydrostatic pressure. The greater the hydrostatic pressure. Hydro means water, but this can apply to any kind of fluid, and that includes gases, which is why we have atmospheric pressure. It's the same reason. So the deeper you go into a liquid, the greater the hydrostatic pressure. That's part A. What about part B, about the density of the liquid? Well, if we replaced this sea of seawater with a sea of mercury. Now, mercury is a liquid at room temperature. It's the only metal that is a liquid at room temperature, and it's very, very dense. You can even float lead in mercury. So this column of mercury, if we were to replace the water with mercury, would have a huge weight pushing down on this area down here, and that would create an even larger pressure. So if the density of fluid, in fact, I'll replace that with liquid just to be consistent. Density of liquid increases, so what can we do? If the density of liquid increases, the hydrostatic pressure at a certain depth also increases. And that's what we need to know. If the density of liquid increases, the hydrostatic pressure also increases. I hope that makes sense. Now, here are a few illustrations of this. You've all seen films where the submarine has to dive to evade the enemy ships, and they go really, really deep, and they're all worried because the hull starts to creak and leak, and cracks start appearing. And the reason for that, as they get deeper, the hydrostatic pressure increases due to the weight of water above the submarine. That pressure acts in all directions on the hull and deforms it, creating all of the damage. What about dams? Why is a dam thicker at the bottom than at the top? Well, if we were to look at a sort of cross-section of this dam, it might look a bit like this. And the water, here's the water. Then hydrostatic pressure increases with depth. So at the bottom, we're going to have a lot of pressure acting on the dam wall. In the halfway up, the pressure reduces until we get to the top, and there's hardly any pressure. So we need to have a lot of strength in this bottom section to resist the forces created by this high pressure. Finally, I'll leave you with an example that you can try at home. If you get yourself a bottle, plastic bottle, nice and big plastic bottle, and you probably want to do this outside. Carefully put some holes on the top and the middle and the bottom. You can put those holes on two sides if you like. Then fill it full of water and see what happens. Well, what you'll see is at the bottom the water is forced out at a great rate. And so, well, my water is actually rising here, but it will fall horizontally quite away from the bottle. The middle hole will come out fairly quickly, but not as quickly. And at the top, it'll be a little dribble, like that. How does this show us that hydrostatic pressure increases with depth? Well, as we go deeper into the liquid, we've got a greater pressure acting upon the area of the hole, and that creates a big force, forcing the water out fast. Here we haven't got such a big pressure, and that therefore means we have not such a great big force, forcing the water out moderately, and finally at the top, got a very small pressure, which means the water dribbles out. And the other holes, the same thing will happen. And what this shows us is that hydrostatic pressure acts in all directions, not just in one direction. And that's why I mentioned that on this diver here, hydrostatic pressure is in fact acting in all directions on their body. I hope you found that helpful. I'll see you in the next flashcard.